Hi, today I'm still going to talk about some basic concept in linear algebra. And today's topic is about determinant and how to use determinant to calculate the solution of ax equal to b. So first of all, let's take a look at our matrix here. So we have a 3 by 3 matrix, and then in R there's a function called det, and then this is where you can call this function to calculate the determinant of the original matrix. And here I'm just going to talk about one of the formula that that is used to so that you can understand how the determinant is calculated here. So first of all, I have this original matrix, and then I put the matrix. I replicate the matrix and then put it side by side, where I have this matrix. So you will notice that the column 4 and column 5 is exactly the same as column 1 and 2. So here is the formula to calculate the determinant of the original matrix. So the product in the diagonal direction. So I have 4, -3, -1. Take the product and then added the product of these three elements, and then added the product of these three elements. And then I subtract the product of these three elements, and then subtract the product of these three elements, and then subtract the elements in these three elements. So the reason I put the matrix, I replicate the matrix and then put it side by side is that I can easily find the elements that I need in the diagonal direction. But if you're already familiar with this method, then you can easily get the elements you need by looking at the original matrix here, without doing the formatting or or to change the layout to get the elements here. But if your matrix is getting bigger and bigger, then it might not easy to find the elements you need. Then you probably need to use some other trick, to make it side by side and then find the elements. So there are many ways to calculate there are many formulas to calculate the determinant of a matrix, but they should all return the same result. But this method is just easier for the way that I normally would use to calculate the determinant. I find it very easy to remember. That's it. But there's also some other ways. So if you're familiar with using other ways, then you can feel free to use other method. But in the end, they should all return the same number to get you the determinant of the matrix. So here I'm also going to talk about some property of the determinant. So if I do row exchange here, so if I do one row exchange by changing row 1 and row 2, so I do 1 times row exchange, it will give me a negative sign here. If I do twice row exchange, then it will bring it back to positive again. So the sign for the determinant depends on how many times you do the row exchange. And here I'm also going to talk about the linear property on the row level of the matrix. So here, as you can see that I added 2 to the elements on the first row of the original matrix, and now my determinant has been changed, and the determinant of the new matrix is actually the sum of the original matrix, and then adding using the determinant of the original matrix, and then also added the determinant of the elements that I need to add. So actually, by adding 2, I can construct a matrix that have all the first column as 2, and then the rest of the column remain the same. So if I added this new matrix to our the determinant of the matrix that we designed here, and then this will get us the determinant of the new matrix here. And same thing for the multiplication here. So I multiply 2 to the elements on the first row, and then that is equivalent that I bring out the 2 before I calculate the determinant. So that so now it's 38. that is also equivalent to 2 multiplied to the determinant of the original matrix, which is 19 in our case. So here are the two linear property to calculate the determinant of the new matrix here. And also the determinant of the identity matrix is just 1. You can all the properties here, you can use this formula to verify and then to see why the sign has been changed, or why you can bring the elements outside and then do the linear combination, and also why you can bring the 2 outside here. So you can all use the basic formula to verify that. And the determinant of a diagonal matrix is just the product of the elements in the diagonal matrix. So 2 multiplied by 4 multiply 6. And then for a linear dependent matrix where there's a 0 vector, there's a 0 rows. So for this, for a linear dependent matrix, and then the determinant is just 0, because when you're doing the multiplication, you'll get all zeros for all the terms if you're using this formula here. And here, when we do, so previously I talked about elimination, Gaussian elimination. So in this case, I'm adding 2 times the third row to the second row. So my new A. So let's take a look at the difference. So here I'm adding 2 times the third row to the second row. So so that I have a new matrix here. But if you take a look at the determinant of the new matrix, I'm still getting 19 here. So if you do a row elimination, then it won't affect your determinant unless you do a division, or you adding elements to one row. So here, if you do a row elimination, like Gaussian elimination, then it will not affect the output of the determinant. You will still get the same result here. And now I'm going to talk about the Laplace expansion. So here, this is my my original matrix here, and now I'm still going to calculate the determinant of the old matrix. But by using this method, I can get simplify my the process. So when you have a bigger matrix, then it would take a long time to calculate the determinant. By using this method, you can get a smaller matrix and then take the sum, and then you can calculate the determinant. Just make it simplified. So here, the method is that, so first of all, I select a row. So in my examples, I use the first row. So I bring out the first elements, so A11, which is 4 here, and then multiply by -1 to the power of the index of the element. So A11, so that the index is 1 and 1. So so that I take the -1 and then to the power of 2. And then I take the determinant of the smaller matrix by removing the first row and the first column, which is I defined it here. So A11 multiplied by -1 to the power of the sum of the index is 1, 1. And then I take the determinant by removing the first row and the first column. And then I go to the second elements, A12, and then multiply by -1 to the power of 1 plus 2, which is the index of these elements in this matrix, and then take the determinant of the smaller matrix by removing the first row and then the second column. So that I will get a 4 by 4 matrix instead. And then I added A13 and then multiply by -1 to the power of 1 plus 3, which is the index for this element here, row 1, column 3, and then take the determinant of the original matrix, but removing the first row and the third column. So I would get a smaller matrix, a 4 by 4 matrix in this part here. So if I use this expansion and then take the sum, and I will still get the same determinant here. So this will just help me to get a smaller matrix and then calculate the determinant. So if you want, you can also verify it by using the same formula, but do it on the second row. So you probably do A21, A22, and then A23, and then here is 21, 22, 23, and then calculate the determinant of the same matrix by removing the second row, first column, and then second row, second column, second row, and the third column. So using this method, it will just help you. It's just another way to calculate the determinant. So like I said, there are multiple ways to calculate the same determinant, either easier or the traditional way. But in the end, you should get the same result. So here I'm also going to talk about the adjugate matrix here. So which is actually the same using this part here. So this is actually called the cofactor of the matrix, and then this is called the minor of the matrix. So I'm going to cover lots of uh, uh, um, points in this video, but you can feel free to pause the video and take a look at the formula here. So here I'm going to calculate the adjugate matrix here. So which is also called the cofactor of the elements here. So so for the first elements here, I'm removing so I'm talking about A11 here, and then calculate the minor of this matrix, which is the matrix that I removed first row and then first column, and then calculate this 4 by 4 matrix here. And then for the second element, 4, 4. And then I have the index is 1, 2, so this becomes negative again, and then calculate the determinants of the remaining 4 by 4 matrix. And then I do the same thing for all the elements, for all 9 elements here. And then I use the cofactor to create the matrix. And make sure that in this case I'm using the column, so it's doing the column wise, so that I'm taking the transpose by taking the cofactor here. So maybe this is a little bit difficult for you to understand, but feel free to pause the video to follow to actually do the calculation here. So again, this is called the minor of the matrix, and then by multiply the -1 to the index of the elements, this is called the cofactor. So I'm using for a 3 by 3 matrix, I have 9 cofactors, and then I'm using the cofactor to construct a new matrix here, which is called the adjugate matrix. And make sure that this is a column wise. So for example, cofactor 1 1, cofactor 1 2, cofactor 1 3. But when you construct the adjugate matrix, you have to take the transpose. So cofactor A11 and then cofactor A12 should be on the second row, and then cofactor 1 3 should be on the third row. So make sure you do the transpose here. So here we have the adjugate function, adjugate matrix here. So this is our original matrix, and then this is our adjugate matrix here, which is the elements are the cofactor of the elements in the original matrix. And the reason that we wanted to build this adjugate matrix here is that it can help us to solve to get the inverse. So here I use the adjugate matrix divided by the determinant of the matrix. So the determinant of the original matrix is 19, and then we use this method to construct the adjugate matrix. So here we use the adjugate matrix divided by the determinants. So this is the matrix, the output matrix. And now let's take a look at the inverse of the original matrix A, and then you can see that this is exactly the same as how we get how we use the formula, the function in R to get the inverse, A inverse, and this is how we calculate by hand to get the A inverse. So by building the aggregate function matrix here and then divided by the determinant, that will give you the the inverse of the original matrix. Here I'm also going to talk about the Cramer's rule. So here this is a new matrix here, and then let me clear everything just to make it easy to understand. So here I have an A and an X. So here I have a linear system here. So I have an AX equal to B. And then the solution is taking the A inverse multiplied by B. So that is the solution for this for the linear system. So here. So the Cramer's rule is that so let's take a look at the original matrix and the matrix that we need. So if we want to calculate the x in the solution, so 3 by 3 elements multiplied by a 3 by 1 matrix, and then we'll get a 3 by 1 result. So our solution has 3 elements here, and then to calculate the first elements in the solution, we just replace the vector b into the original matrix. So I put 1, 0, 0, and then the remaining column are the same. So I use this matrix, and then I divide it by the determinant, and that will give me the x value. And again, I replace the second column with my vector b, and then I use the determinant of that matrix to divide it by the determinant of the original matrix. And then I substitute the third column with my vector b, and then I use the determinant of the new matrix divided by the determinant of the determinant of the original matrix, and I'll get the solution of my third element. So now let's combine all the elements here into one vector. And now also let's take a look at the solution that we calculate by using the A inverse multiplied by B. And then you'll notice that they are the same. So the Cramer rule is that another way to calculate the solution of AX equal to B, and then using the concept of the determinants. So here in this video I talk about the formula to calculate the determinants, and then also some property on the determinant of the matrix. And I also talk about the Laplace expansion. This is also another way to calculate the determinants. And I also talk about the Adjugate matrix here, which is very helpful to calculate the A inverse. And I also use the Cramer rules to talk about how to calculate the solution of AX equal to B. So this video is all about matrix, and then there are lots. So you can see that the determinant of a matrix is a very important concept. It can help you to do a lot of things, and so make sure you pause the video, take a look at the formula, make sure you understand the concept, or to understand the formula. So thank you very much, and let me know if you have any question.